have discussed or you have done the contest, and let's see the result. Discussed. Let me share my screen. Okay, here it is. I gave you 3 problems, and okay, Matt got full score. And for the first problem, it was easy because since all of you got accepted, then let's just move to the second problem. Okay. For the second problem, okay, Mutahir got 18 points or maybe 20 points. Okay. It means you solve the subtask. So let me ask Mutahir, how was your solution? Okay, welcome Hassan Arif. Okay. We are discussing problem B. And okay, I think Hassan also got 20 points. So how was your solution for this subtask? Yes, just brute force, right? Yes, it is easy because it's okay to solve it in ONNQ or even ONQ log. Yes, this is the easiest of that. And then how to speed it up? Any idea? Any idea to speed this up? Here, given some range, and we want to find the maximum value of h, right? Maximum h such that the number of value greater than or equal to 8 is at least 8, right? Like it is. The answer cannot exceed square root. I don't think so. Why it cannot exceed square root? Here, at least 8 times. And it's okay if it is more than 8. And given pi is the number of citations, and the number of citation is up to 20, sorry, 200,000. In the worst case, the answer can be n, right? Okay, yes. For example, if all pi is equal to n, and we are asking for L equal to 1 and R equal to N. So what is the answer for this case? All Pi equal to N. Okay, yes, the answer is equal to N. Okay, welcome, Hassan. Sorry, Gamas Hassan. I think Gamas got accepted on the second problem. So, what was your solution? Okay, Moss algorithm. Good. Yes, we can use Moss algorithm, and the complexity will be ON square root, right? Okay, that's good idea. What about Ahmed? Okay, he used most algorithm as well. But actually, I have another solution with time complexity only O n log n. Okay, can you predict? Uh, yes, online. We can solve it online. Okay, so it is faster than most algorithm, and also it is online, not offline. Yes, we can use persistent segment tree. Okay. Actually, there is another solution, but not better, I think. There is another solution with complexity n log square n, but it is offline using, I think maybe just use segmentary or Fenwick tree, but with parallel binary search. Okay, but it is worse than persistent segment tree. Okay. Do you know how to implement persistent segment tree? Okay. And do you know how to use it to solve this problem? Okay. Wait, I think the time complexity will be n log square n, but the memory is n log n, and it is online. It means we can directly find the answer for LR before the next one. Okay. Okay. Yes, we haven't discussed about persistent segmentary before. Okay. Yes, Dishan got an idea. What if we use binary search on the answer, and then we want to find the number of occurrence greater than or equal with weight. Yes, the idea is like that. That's how to calculate the number of occurrence. Persistent segmentary. Okay, yes. Or there is another solution other than persistent segmentary. We can also use trains tree. So we have a segment tree, and for every node, we store a sorted array of P. So we can easily lower bound and upper bound the array. So we can easily know the number of occurrence greater than or equal to something. Okay. And the complexity, wait, but I think the complexity will be n log cube because we need log for binary search, and then we need log number of segment in segment 3, and we need another log for doing the, sorry, I think lower bound on the array. So it will be n log cube, and I think it will got time limit exceeded. Okay. And for segment 3, it is easy. We can do this. Wait. For persistent segment 3, we can easily store all version of segment 3, right? So initially the segment 3 is empty, and then we will update them one by one. Starts from the highest value. We update it, change it into 1, and then update the second maximum, update the third maximum, and so on. So we can easily binary search the answer. For example, let's say the answer is this, and this is a segment 3 consists of every value greater than or equal to 8. Okay. Then we just need to find the sum, right? Okay, you got it? Is it understood? For example, we have all version of segmentary. Okay, we can use persistent segmentary. So actually in persistent segmentary, if we update something, we can still store the previous segmentary. So we have just like n segmentary, but we just need n log n memory. But we have n segmentary. Okay. And actually there is another okay, I got another idea. But this is offline, I think. We can find the answer for its query based on R. So we will pre-compute, but wait, is it possible? Hmm. Okay, never mind. I think that's not a good idea. Okay, let's go back to persistent segmentary idea. So before that, I have to explain to you what is persistent segmentary. So persistent data structure means a data structure such that we still store the previous version. So we can easily undo the operation or something like that. Okay. So the idea is like this. Suppose that we have a segmentary. We have a segmentary like this. This is the initial segmentary or version 0. And then if we want to create the next version by updating the previous version, okay, by updating a value in the previous version. So, if we update this value, then some values might change, right? So we have to create some new nodes. And in the worst case, there are log n nodes, right? And what about the others? Since everything here is not changing, so we can assume the left child of it is this. Okay, you got it? Okay. And then all values here is not changing. So we can easily assume the right child of this is this. And then the left child of this is this. Okay. Is it understood? Okay. So basically we create a new segment tree, but it just consume log and memory, right? Okay. So welcome, Hayan. we are we are discussing uh we are discussing about persistent segment tree now. If we discuss it before, I think I have discussed persistent segment tree with seniors. Is it correct? Okay, good. Waalaikumsalam. Okay. So basically in persistent segment tree, if we want to update some value, we create another segment tree instead of editing the old version. So instead of editing the old version, we want to create a new one. So the previous version is persist. That's why we call it persistent segment tree. Okay. And we just need to create some new nodes, not all nodes. We just need log n nodes, not n, but log n. Why? Because for some value that is not changing, we can use the previous version. Okay. After having a new version, we can edit into the next version by again using the previous value. For example, we will update this. So the left child is this, and the left child of this is this, right? And then the right child of this is this. Okay, you got it? Okay. Again, we just need log and memory, but we create a new version of segment tree. And here we can easily querying the range and also checking the values or something like that. Just using the basic function, we can easily querying just like basic segment tree. Okay. Because it is just like regular segment tree, right? We have a root, we have right child, we have left child, and so on. Okay. Then how to implement this? Actually, it is we can use pointer to implement this. But if you are not familiar with pointer, we can also use integer, just like manual pointer. Okay, which one you prefer? Using pointer or just manual indexing? Let me show you how to implement this. Okay. Let me create a pool. Okay. Okay, I have created a pool. You can choose which one you prefer, using pointer or without pointer. Okay, good. I think 50-50, 50%. Okay, now without pointer is more than pointer. Okay, there is a question from Vision. Left child, V. Manual indexing, I mean, just like this. We give an index for each node. For example, this is node 1, node 2, node 3, node 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And let's assume this is 16, 17, 18, 19, 20, and then 21, 22, 23. Okay, just like this. Okay. If we will not use pointer, we need to create manual indexing like this. But if we use pointer, it will automatically do that. Actually, the idea are same, but just different implementation. Okay. Okay, I think most of you prefer without pointer. Then it means we have to prepare. Wait, we have to prepare some arrays. This is the input. And this is the value of segment 3. We need n log n actually. The size of segment 3 is n log n. Okay, this 2e5. So value of log is how many? 18. Okay. Yes, 18. But we need another 4 because for the initial values, right? So we need 4n or 2n actually. Or yes, for example, 2n for initial values and q times log n for the next values. So basically it is 2e5 times 2 plus 18, right? Okay, so let's make it 4e6. Okay. Value and then what should we do? We need L and R, left child and right child, like this. Okay. Okay, yes, we can make it xn times 22. Okay. Yes. So we will do this. We have n version, I think. Okay. Yes, actually, since we will make a manual index, the index is not like this. It's not 2x plus 1. But we will create the index manually. So basically, actually 2n is enough, but 4n is more than that. So length is less. So, 4n is because uh, we use the indexing mechanism like this. But if we make the index manual index like this, then the number of node is exactly 2x minus 1. Okay. Do you know why? Because there is a tree with n leaves. A tree with n leaves means it has 2n minus 1 nodes. Okay, exactly 2n minus 1 nodes. I mean binary tree. Okay. So actually 20 is enough. But if you are doubt, we can make it 22. Okay. You got it? Actually 20 is enough. But but it's okay. Okay, we will see later from the implementation. And then we have N, Q, and also what's next? Array of P. I think since we want to sort them, we need a pair, I think. And we will sort them. After that, we want to make permutation. I think we need to update from the biggest value. Because we want to find the number of whole value that greater than or equal to something. Okay. Maybe let's just do this. Where n+1 is the initial version. Just build like this. This is the initial version. And then version I is update. The result of an update, right? Update from the previous version. And what is next? We want to update in position pi.second by 1. Okay. Okay. We have created all version. Now we want to answer the queries. Okay. And we also need to wait. Okay, it's okay. Wait. I think it will be better if we do this. We have a vector of p like this. P consists of all index that has such value. Okay, like this. And then we will just do this. We will start from maximum p, for example. Maximum p is 2e5. Okay. So just build like this. And then let's start from maximum p till 1. We want to update for all vector I like this. Okay, we will activate 1 like this. What is next? Okay. Compare the next version is equal to this version. Okay. After that, we want to do a binary search like this. I think 1 is always valid. Wait. 1 is always valid, right?
Yeah.
So we don't need version 1. We can start the painter search from 2. Okay. How to check it? We just need to check a version of mid from X to Y. And if the sum is greater than or equal to mid, it means, okay, it means answer is equal to mid at least. But we will try the higher values. Otherwise, we need smaller values. Okay. So how it works? At first, okay, when we build a new segment tree, we can do this. And the x is equal to id plus plus, or I think this would be cnd. Okay. And then if L equal to R, it means it is the leaf, right? Value X is equal to 0. And then return. Return X here. Otherwise, we have to divide or split into two children. We will do this. Left X is equal to build L mid. Right X equal to build mid plus 1 R. And then value X is the sum of value left X and value right X. Okay, you got it? Any question about this? So the return is equal to the index of the node. Okay, is it understood? Okay. Then for query is a 3, and then X and Y, and then LR. As usual, if X is less than or equal to L and Y is greater than or equal to R, then just return value TR. And then if x is greater than r and y is less than l, or I think return 0. Otherwise, return query left child plus query right child. Okay. Is it understood?